Welcome to this video on St. Venant torsion. This is one of several videos in a short course on structural members posted at terje.civil.ubc.ca, Toolbox, a website that contains notes, examples, and algorithms for structural analysis. Please visit the website for more videos and other material relevant for this course. In the context of structural analysis, torsion means that a beam or frame member is twisted about the longitudinal axis of the member. This slide visualizes torsion in several ways. The double arrow at the top of the slide is one way to indicate torsion. A double arrow means rotation about the axis of the arrow. The symbol T is used for the torque, which in this video is the resultant of shear stress. The Greek symbol phi denotes the rotation. That rotation is further illustrated below. This is a beam with a wide flange cross-section subjected to torsion. The cross-section shown in the gray color on the right-hand side rotates by an amount denoted by the symbol phi. Torsion is further visualized by the solid and dashed blue lines. The solid line is the top flange. The dashed line is the bottom flange. There are two types of torsion. One is called St. Venant torsion and the other is called warping torsion. St. Venant torsion is formulated in terms of shear stress. This means that St. Venant torsion lets the applied torque be carried by shear stress in the cross-section. The other torsion theory, referred to as warping torsion, includes axial stress. Although warping torsion is the subject of another video, you may here see that the bending of the flanges of this cross-section causes axial stress at the left-hand side of the beam. As a matter of fact, the theory of warping torsion has many similarities with Euler-Bernoulli beam theory, which is also formulated primarily in terms of axial stress. The next slide gives an overview of the equations that will be derived in this video for St. Venant torsion of two different member types. One has a circular cross-section that is either solid or hollow. The other type of member that is considered in this video is general, in the sense that it can have any type of cross-section. The typical application is what we call members with thin-walled cross-sections. That includes the wide flange cross-section and the one-cell cross-section shown here. As we do for any boundary value problem in solid mechanics, we will establish equilibrium, material law, and kinematic compatibility equations. However, notice that we will work with shear stress instead of axial stress in this video. That means the section integration equation entails the integration of shear stress over the cross-section. It also means that the strain is shear strain. The notation adopted in this video is shown here. X is the longitudinal axis of the member. Mx is the distributed torque along the member. The Greek symbol phi is the rotation about the x-axis. J is the cross-section constant for St. Venant torsion. G is the shear modulus, which is the Young's modulus divided by 2 times 1 plus the Poisson ratio. Tau is the shear stress and gamma is the shear strain. Equilibrium is established by considering an infinitesimally short segment of the beam with length dx. The resultant torque from the distributed torque is mx times dx. The torque, T, on the left-hand side cancels with the torque, T, on the right-hand side. Only the infinitesimal change in the torque remains. The result is that mx equals minus dt over dx. The section integration for the circular cross-sections, which is addressed first in this video, is shown here. In case the cross-section is hollow, we work with two radii. Ri is the inner radius and Ro is the outer radius. The integral is from Ri to Ro because the integration around the cross-section is taken care of by the parenthesis 2 pi r, which is the circumferential length of a circle. Tau is the shear stress and r is the moment arm from the center of the cross-section. The material law in St. Venant torsion is shown here. The shear stress, tau, is equal to the shear modulus multiplied with the shear strain, gamma. Kinematic compatibility is illustrated on this slide. The objective is to establish a relationship between the shear strain, gamma, and the rotation of the cross-section, denoted by phi. The figure shows an infinitesimally small segment of the beam at a distance r from the center. Notice the shear strain gamma, and notice the infinitesimal rotation d phi. By using the geometrical rule that the length of a segment of a circle is equal to radius times the angle spanned by the circle segment, we can make the following two statements. First, the line pointed to by the red arrow is equal to gamma times dx. Second, the line pointed to by the red arrow is equal to d phi times the radius, r. That equality leads directly to the kinematic compatibility equation shown here. The derivative of the rotation, phi, with respect to x is equal to gamma over the radius, r. The next slide shows a summary of the equations that were derived on the previous slides. They are also combined in order to obtain the differential equation for St. Venant torsion, marked with the green color. Notice that the cross-sectional constant for St. Venant torsion for members with is circular cross-section is defined in the red box. The equation that combines section integration, material law, and kinematic compatibility, but omits equilibrium with externally applied distributed torque is also derived, shown in blue. This form of this boundary value problem is somewhat similar to that for truss members. The equation in the blue circle indicates that the rotation along a beam member that has a torque applied at one end varies linearly, just like the longitudinal displacement of a truss member subjected to an axial force at the end also varies linearly. In fact, the general solution to this differential equation is as simple as that in the video on truss members, so it is omitted in this video. The equations marked with the green and blue colors on this slide are generally valid in St. Venant torsion, also when we now start addressing general types of cross-sections. To that end, the next slide introduces the concept of a stress function. It is an entity that appears elsewhere in the theory of elasticity, and it is an auxiliary quantity without direct physical meaning. Rather, a stress function is defined by the fact that we can differentiate it to obtain the actual stress. The prominent use of stress functions in general St. Venant torsion should make us question why the theory is named after St. Venant. That is because St. Venant formulated the theory in terms of an unknown function that represents the axial displacement at any point of the cross-section. It was Ludwig Prandtl who reformulated the problem in terms of a stress function, which is the way we address torque carried by shear stress today. On the slide, the stress function is denoted by the letter P. It is a function of the cross-section coordinates y and z. The figure shows that y is the horizontal axis in the cross-section, while z is vertical. The coordinate system shown on this slide is adopted in all the notes that are posted at terje.civil.ubc.ca. U is the displacement in the x direction. V is the displacement in the y direction, and W is the displacement in the z direction. The first thing we need to understand about the stress function is that we obtain shear stress by differentiating it. In fact, the shear stress in one direction is obtained by differentiating the stress function in the perpendicular direction. A derivative is written in two different ways on this slide. The standard notation dp over dz is here written by a comma followed by the letter z. This notation is common in index notation. Notice that the derivative of the stress function in the z direction gives the shear stress tau xy. The negative of the derivative of the stress function in the y direction gives the shear stress tau xz. The direction of those shear stresses is shown with the blue color in the figure. The first index of the shear stress is the coordinate direction that is perpendicular to the plane that the shear stress acts on. The second index is the direction of the shear stress itself. You may now be puzzled by the fact that we differentiate a function in order to get stress. Then keep the following two facts in mind. First, the stress function itself has no physical meaning. It is simply an auxiliary function. Second, the minus sign and the way the stress function is differentiated are defined in that way for the sole reason that the equilibrium equations at any point in the cross-section is then automatically satisfied. This is the ingenious feature of the stress function that makes it useful. Let us say it out loud once more. The stress function is defined so that the stress we obtain when we differentiate it in a certain way automatically satisfies the equilibrium equations of solid mechanics. You may not be familiar with index notation, although it is employed several places in terje's toolbox, including in the mathematics notes on the basics page. Also, you may not be familiar with the equilibrium equations of three-dimensional elasticity theory. Those equations are written in index notation here. The zeros at the end of the equations imply equilibrium in the three-axis directions. On the right-hand side, the stress function is utilized to express the shear stresses. In that case, all three expressions turn out to be zero. That is because of the following reasons. First, the stress function does not vary with x second. All axial stresses are zero in St. Venant theory. Third, the shear stress tau yz is zero because the cross-section is assumed to retain its shape. In summary, the use of Prandtl's stress function as a surrogate measure of stress automatically satisfies the equilibrium equations. On the next slide, we formulate boundary conditions for the stress function, with the hope that we may soon look at actual expressions for the stress function. The shear stress on the surface of a structural member is obviously zero, because there is thin air adjacent to the member. This translates into a boundary condition for the stress function. To formulate this boundary condition mathematically, let S be the coordinate that follows the edge of the cross-section. Let R be the axis that is perpendicular to S, and let alpha denote the angle between the y-axis and the edge of the cross-section, as illustrated in this figure. The figure on the left shows the shear stress perpendicular to the edge of the cross-section. The figure on the right shows the relationship between differentials for the different axes, which we will soon use in the equations below. The fact that there is no stress on the free surface is expressed in the first equation. The second equation shows how that stress in the r direction is obtained from the stress function by differentiation in the s direction. As a result, the fact that there is no stress on the free surface translates into the following boundary condition for the stress function. The derivative of the stress function along the s-axis, which follows the contour of the cross-section, must be zero. Another way of deriving the same result is to use decomposition of the shear stresses tau xy and tau xz. That is done in the rightmost equation. In short, the derivative of the stress function must be zero along the edge of the cross-section, which implies that the stress function must be constant along that edge. For convenience and without loss of generality, this constant is set equal to zero. When observing the simplicity of this boundary condition, it can be remarked that St. Venant's formulation of the theory, in terms of a function that describes the axial displacement in the cross-section, introduces a more complicated equation for this boundary condition. With Prandtl's stress function, one simply needs to assure a constant value along the edge of the cross-section. The next slide visualizes a few candidate stress functions. The stress functions are shown with a gray color. On the left-hand side is half-cylinder that has zero value on the vertical edges of the cross-section. On the horizontal edges of the cross-section, this stress function is not zero. It is not even constant, and that violates the boundary condition that we established on the previous slide. However, this stress function is actually used in practice when the length of the horizontal edges of the cross-section is much smaller than the length of the vertical edges. In that case, the error caused by the violation of the boundary condition is negligible. The stress function in the middle of this slide satisfies the boundary condition because it is zero around all edges of the cross-section. This stress function is used for hollow rectangular cross-sections because it satisfies the boundary condition also on the inner edge of the cross-section walls. We see that this stress function is constant around the edges of the cell of the hollow cross-section, which does indeed satisfy the boundary condition. The stress function on the right-hand side looks like a cone that is zero around the edge of this circular cross-section. It would have been even better to visualize a similar shape that looks more like a bubble, with continuously varying derivative, because that is a commonly used stress function. The word bubble is helpful for visualizing shape functions. Specifically, think of a membrane that is attached to the edges of the cross-section, whatever shape it may have. Then imagine blowing wind on that membrane so that it bulges outwards, like the shapes shown in this figure. You are then visualizing a valid stress function. Remember, you get the shear stress in any direction by differentiating the stress function in the perpendicular direction. On the next slide, we address section integration. Integration of shear stresses multiplied by their distance to the center is shown in the equation at the top. The next equation shows how those shear stresses are formulated in terms of the stress function. The integral is simplified by invoking integration by parts. The first term in the integrand is partially integrated in the y direction and the second term in z direction. The result is as shown here because the boundary integrals vanish on account of the fact that the stress function is 0 around the outer edges of the cross-section. This result, which says that the torque at a point along the beam is twice the volume under the stress function, is a cornerstone of St. Venant torsion theory. It is important to understand that the factor 2 is generally valid. For certain cross-sections, such as the open thin-walled cross-sections, equilibrium of the shear flow appears to give a torque that is half of this value. To address this puzzle, it is first noted that the integrand of the integrals on this slide consists of two contributions from shear stress in perpendicular directions. For certain simplified stress functions, such as the one used for thin-walled open cross-sections, which is the half-cylinder shown on the previous slide, the stress at the short ends is neglected, which causes the apparent anomaly. In actuality, there are shear stresses at those locations. In fact, those contributions double the torque because their moment arm is large. In Chapter 10 of their 1969 book on theory of elasticity, Timoshenko and Goodyear acknowledge that the small shear stresses that are sometimes neglected can have an appreciable effect because their moment arm is substantial. They also suggest further reading by mentioning that the question was cleared up by Lord Kelvin in Kelvin and Tate's Natural Philosophy, Volume 2, page 267. The material law for the different coordinate shear stresses is identical to the material law presented earlier in this video. For that reason, we move directly to kinematic compatibility. As a fundamental postulation, it is assumed that the cross-section retains its shape during torsion. The two equations at the top of this slide express that fact. The displacement in the y and z directions are directly determined by the rotation of the cross-section. It is also assumed that the axial displacement in the cross-section, u, only varies with y and z. The original formulation by St. Venant goes to greater lengths to characterize the axial displacement in the cross-section. However, this is circumvented in the theory formulated in terms of Prandtl's stress function. With these assumptions, the 6 kinematic compatibility equations for general three-dimensional theory of elasticity comes out as shown on this slide. The first strain equals 0 because u is independent of x. The second and third strains equal 0 because no deformation of the shape of the cross-section is allowed. The shear strain at the bottom of this slide is 0 because the cross-section does not change shape. A summary of the equations derived on the previous slides is shown here. Notice that the stress function, P, appears in the place where we normally see the stress. Also observe how the shear stress is derived from the stress function, allowing the figure to continue on the right-hand side with the formulation of the material law in terms of stress. In the circles marked with the green and blue colors, we see equations that appeared earlier in this video. These are template equations that define what the cross-section constant, J, is. In other words, the equations in the green and blue circles are not explicitly derived on this slide by combining other ingredients shown here. Rather, they express how the other equations on this slide, when combined, feed into the evaluation of the cross-section constant for St. Venant torsion. In other words, the equations in the green and blue circles simply organize the notation for any St. Venant torsion problem. What we have not seen before in this video is the equation in the red circle. It expresses material law and kinematic compatibility and is derived at the bottom of this slide. The kinematic compatibility and material law equations, combined with Prandtl's stress function, yields the two equations on the left-hand side. It turns out that these two equations can be combined into one. By differentiating the first with respect to z and the second with respect to y, the derivative of u with respect to y and z becomes a common quantity that facilitates the merger. The result is shown on the right-hand side. This is the general differential equation for St. Venant torsion for members with arbitrary cross-sections when Prandtl's stress function is employed. Put another way, this is the differential equation that governs the stress function. It is noted that this differential equation, marked above with the red color, does not include the section integration equation, which says that the torque is twice the volume of the stress function. That equation, marked with a solid black line, is the other key equation in St. Venant torsion theory. Although cross-section analysis is addressed in another short course at terje.civil.ubc.ca, Toolbox, the next slide gives a preview. The objectives of most cross-section analyses are to calculate cross-section constants, in this case J, and stresses, in this case tau xy and tau xz. In this case, the stresses are easily calculated once the stress function is known, as shown on previous slides. This slide gives a sense of how the cross-section constant, J, is calculated once the stress function has been determined. To that end, consider the two main equations from the previous slide, marked with solid black and red lines. Both equations are formulated in terms of the stress function. They are combined by substituting them into the general St. Venant torsion expression marked with the blue color. The section integration equation fits on the left-hand side. The differential equation fits on the right-hand side. By solving for the cross-section constant, J, we obtain the expression marked with the orange color at the bottom of the slide. The volume of underneath the stress function is here denoted by V in short. The main objective when solving practical problems in St. Venant torsion theory is the determination of the stress function. This is done for different cross-section types in the notes and examples posted at terje.civil.ubc.ca Toolbox and in a short course posted there on cross-section analysis. Thanks for watching this video. Please visit terje.civil.ubc.ca Toolbox for more videos and more material relevant for the modern structural engineer. See you soon.